Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm a senior contributing editor with Data Science Central and also chief data scientist at Data Magnum. I'd like to start off our event today by thanking Pivotal for sponsoring today's event. Pivotal is a longtime supporter of Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to view them, I encourage you to take a look as they provide some very useful insight into a wide variety of topics of current interest in our data science community today. Today's webinar is entitled The Internet of Things, How Data Science-Driven Software is Eating the Connected World. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have one panelist that I'll introduce in just a minute. There will be 10 to 15 minutes of QA following the presentation, and this event is being recorded and will be available on datasciencecentral.com in the next few days following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speaker, Sarah Aerni of Pivotal. Sarah is a principal data scientist at Pivotal, leading the San Francisco practice. She executes projects with customers from pharmaceutical companies and healthcare providers to financial institutions. Before Pivotal, Sarah obtained her PhD from Stanford University in biomedical informatics, performing research at the interface of biomedicine and machine learning. She also co-founded a company offering expert services in informatics to both academia and industry. Thanks for being with us today, Sarah. We're looking forward to your presentation. The Internet of Things will forever change the way businesses interact with consumers and each other. To derive true value from these devices and ultimately drive the next fundamental shift in how we live and operate requires the ability to pool this data and build data models that are real drivers of significant action. In today's webinar, Sarah will present a series of use cases illustrating how such devices and the data from these devices drives real impact across industries. From smart sensors to connected hospitals, each example will highlight the fundamental concepts of success. You'll learn about starting with the basics, how data science drives action and outcomes, avoiding the obstacles, how to avoid the pitfalls that prevent models from driving real action, and building your toolbox and what tools are available. So Sarah, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thanks so much for the introduction. So my name is Sarah, as was mentioned, and I'm hoping to provide some insight today into the data science side of the Internet of Things. So I want to start off just with a view of what is happening today in the world for most of us, at least, who have smart devices in our lives. So almost everyone, I would say, has a smartphone, probably on this call. There are, of course, a lot of other devices that you can have in your daily life, Fitbits, for example, other types of wearables that record information about what's happening in your day-to-day. Of course, there are some more advanced devices like cars, for example, the Tesla, that collects a lot of data about what's going on. These devices even live inside our houses and try and control temperature to keep us more comfortable and sort of be more efficient with energy. Now, those devices are smart. They speak to us. They let us know what's happening in the world around us or to ourselves. But what would be even more interesting would be if those devices spoke to each other directly and communicated what was going on and drove action that would make our lives even better, even easier. So one simple example with Tesla, actually, is one individual who's been working on what's called Visible Tesla. What he does is he has the Tesla itself hacked, essentially, to communicate with him directly on his phone as needed in order to drive some sort of an interesting action. For example, if he pulls up in a Safeway parking lot, it might tell, which is a grocery store, it might tell him, oh, you need to get your bags out of your trunk. So it's aware of what's around it and what's going on. There might be other things where maybe if you're arriving home, the Tesla might be able to tell in advance to the Nest, hey, let's start warming up the house. All of these instances are actually useful for devices to communicate to each other, so that can actually make our lives a lot easier. Other examples that exist currently today would be an alarm clock that goes off and tells your coffee machine to start brewing. Of course, refrigerators that detect when something went bad and maybe add on your grocery list on your phone that particular item should be purchased again this time around. So they're all great. They could improve our day-to-day lives. But actually what we would like is for IoT to extend beyond the conveniences of our daily lives and maybe be able to prevent disasters like oil spills or potentially healthcare-related ones that we'll be discussing as well today. The reality is that aside from our smart devices, in all of the industries, there are simply billions of data points coming out of different devices, different sensors in our environment. That could be from video surveillance, which captures data continuously about what's happening, to something like the stock market, which of course is giving us information about changes in pricing, but also increasingly in the biomedical domain, other types of more advanced techniques that are evolving and being created in sort of very rapid pace. For example, on the gene sequencing side, which simply allows us to understand not only kind of mutations in our own bodies, but potentially what's happening around us. For example, in food quality, to try and understand if it's been contaminated in any way by detecting presence of genes that are belonging, for example, to E. coli. Now, in order for any of this to work, for us to be able to use that sensor data, there has to be a place for all of this data to be aggregated, collected, and for us to build models to act upon those. So aside from discussing a bit around how to build models, I also want to make sure that part of our consideration in today's discussion actually also centers around what is possible. So it's important to be able to respond at the right time to a particular signal that's being processed in order to actually go ahead and drive something that can have an outcome that's positive and beneficial. So really being able to bring the data together, formulate some sort of a problem on what to do to solve that particular challenge, and then actually building models around it to allow us to drive that action. Here at Pivotal, we think a lot about the data lake as being the right place to bring all of that data together, generally allowing you to bring together structured and unstructured data into for example, a Hadoop environment, and then being able to build models in that, but also to have a low latency response when needed on particular types of models. And we'll discuss those as we go along. Now, what are the challenges in terms of dealing with data? Let's think about one simple example. So this is an example of a sensor, actually, that can be attached to your phone, a live core. And what it does is let you essentially monitor what's happening with your heart. And it's really meant to be able to detect something like a stroke. Now, we see here on the left at the top, it's sort of a feed, a sensor coming off essentially is looking at what's happening with your heart. And what has to happen is you have to take this data, which essentially is just a stream, and convert it into an action. So how do you actually label when something is indicative of a stroke or something going wrong? What you then, of course, would want to do is drive some sort of an action. So LiveCore lets you see on your phone, hey, this is great, nothing is really wrong, potentially something's abnormal, go see your doctor, or it's bad, you may be having an incident, a stroke. In that case, maybe it should be phoning for an ambulance. You might be wanting to be told where the nearest hospital is. Even in an intermediate stage, you would want to alert your physician to let them know, hey, there's something abnormal here, should be checked out. So in today's discussion, what we want to talk about is kind of how that data is collected, where it could be stored and processed. How do you actually distinguish that signal that, for example, here might be indicative of a stroke from something like noise, where it's just a known abnormality or a change resulting from maybe movement or some other healthy activity? How could you build a predictive model around this to predict when something might go wrong in the future? And of course, when the right time is to take action. We don't want to be calling for an ambulance unless it's actually needed. So in order to talk through these, what I'll consider critical considerations for successful modeling, I'll be walking through a set of use cases. That's usually the best way to talk through these ideas at a high level. So we'll start off with an oil drilling example. It might not be an area that you've worked in before or even thought too much about. It certainly wasn't an area that I thought too much about. However, it's pretty intuitive, and we'll be able to talk about how to build predictive models at scale. Tons of data is coming from these sensors, so we really need to understand how that data can be processed and used in one very large model. Next, we'll go through an example in vaccine manufacturing. Manufacturing is also an area very rich in sensors. And here we'll talk a little bit about the trade-offs between modeling accuracy and timeliness. So again, what we discussed about the right time to take action in order to drive an outcome that's wanted. Finally, we'll talk about healthcare and treating patients, also generally a pretty relatable space. A lot of people have experience with it in one way or another. And here we'll talk a little bit more about how to derive insights from models. So once you build models, yes, of course they can drive low latency automated action, but they also might indicate where you could go through a process change, something that you might want to introduce into the process or where you might want to make changes in order to drive a better outcome. Through all of this, of course, we'll be talking about the data-driven paradigms, any data cleansing and feature engineering required in order to be successful in any one of these types of projects. So let's turn first to the oil drilling example. In the oil drilling, the oil and gas industry, exploration and identification of new places to essentially source oil is very important. And there's actually a large amount of sensor data that has existed in this space for quite some time. And what really is desired here is to come up with data-driven approaches to improve their operation. So essentially, how do I get to that oil faster? Now, when you think about what happens in an oil rig here, really what you're wanting to do is drill into the earth essentially as quickly as possible, as efficiently as possible, waste as little money, for example, damage any sort of equipment, of course, make sure that you drill very quickly through so that you can get to that oil and move on to the next site where you would want to start extracting again. Now, on the operations side, there are a lot of things that you can kind of predict in order to figure out how to get to that oil as quickly as possible. And actually, specifically, we'll be talking about the rate of penetration, which is how quickly you will get into the earth, so how quickly you get down to that oil source. Because, of course, the shorter time of production could lower cost, of course, in terms of labor, but also would increase that production, so more money, less cost. Essentially, what you want to do is identify kind of the parameters, so what particular drill bit, what pressure, for example, you might want to apply in order to drill as quickly as possible. You might want to come up with an initial approach. Some of the things that could vary, for example, would be the soil type that would affect the types of decisions you make in order to optimize this drilling. And, of course, potential reduction to damage in equipment. On the predictive maintenance side, it turns out that any time there's sort of a failure and you have to stop drilling, those are estimated. There's a blog available here at the bottom that speaks to it, that there are billions of dollars wasted in this space every year. And so actually having an early warning system that allows you to predict it, that there will be an issue and therefore go and maintain the equipment before anything goes really wrong would be beneficial. So those are just a couple example use cases where you might use sensors to try and build models. But let's talk through a little bit more concretely about what's required in order to work with this type of data to build a model. I'll go through 3 steps here in particular. I'll talk about how you actually integrate the different data sets. Of course, there are multiple sensors and multiple data sources that are being used. So how do you bring those together? How do you clean that data up? Next, we'll talk through feature building. That's actually, features here indicate the variables that are going to go into your model. So how do you extract those from the data set? And then finally, the modeling itself. How do you build those actual models? What are sort of the underlying methods to allow the computation to occur at scale? So let's start off with integration and cleansing. One very simple example, in the drilling space, there are sensors that are coming off of the rig itself. And there are billions of those coming in. So we have, for example, again, the rate of penetration, how quickly I'm drilling into the earth, RPMs, rotations per minute, and the weight on bit, which essentially, if you think you push very hard onto a drill and it spins very quickly, you would get into the earth quickly. So something in terms of building a model that might be important. On the operator side, this is actually data that's not being collected from sensors. This is the person or the sets of persons who are operating that rig. Here we actually don't have as many records. Turns out we only have thousands. Those could be if a failure occurs, what the particular failure was, any sort of notes around it, component details, drill bit details, what type of drill I'm using. Those data sets very simply need to be integrated, which is something that you want to consider. So when we look at here, the sensor data, look at time and that rate of penetration, the ROP that we were talking about. Something that's coming from the operator might actually be drill bit changes that are occurring. Here we show sort of orange being one drill bit, green another, and at the time that they were swapped. So very simple. This seems very straightforward because it sort of is, but you have to have a consideration around how to apply that particular variable and the presence or absence of it across that time series. This is one very simple example. There can be much more complex example where things may be changing over time and you might have to interpolate along the way. Now, what I think is even more interesting, though, to consider is the cleansing component. So, of course, it's important to be able to understand what is happening when you have a sensor like this. So weight on bit might be an example of a sensor that's actually variable. It's recording data, and as we can see here, there are sort of two general types of weight on bit that we're seeing. They're essentially levels. And there might be some pressure that's being applied by the operator's control and decision, but there's some variability as to what's being measured, and that could be, actual variability coming from changes in the environment around it, or it could be the sensor itself that is imperfect, which is frequently the case. Now, to a human, I think it's pretty easy to see that there are sort of two weights on bit that we can see here that are split sort of near 1/3 mark of that total data set. However, let's consider what you would want to do if you're trying to build a model off of this. If you want to work with this data, you might be wanting to split along the mean to see what the two general classes are that we have here. What would happen is you would end up with this division where the left and right, as you can see, are actually being split in a way that's nonsensical. When in reality what you want to do is split it sort of along the line here where you can see left and right, there are definitely two different general weights on bit. Now, in these instances with sensor data, one of the most important things to do is actually to go ahead and do something with the sensor data, actually specifically cleaning it up so that you'll be able to see what the averages across a window are, for example. And that's specifically what you would be able to do then, is smooth that data. So here's an example of where we simply took a window of 10 before and 10 following, removed the max and min, and took the average across that window. The reason we take the average in this particular instance is just for speed of computation. That's something that can be done very rapidly, and when you think again about having billions of rows, you have to have some consideration as to what's computationally feasible. Of course, a median is generally preferred. Now, that's just one particular example of how sensor data needs to be cleaned up. But as we move forward, we also have to think about the features themselves that we're building. So in addition to needing to clean up that particular data set of sensors, we also need to consider the fact that sensor data is continuous feed, and how do we build models off of it. So let's think about the failure that we discussed as one of those examples earlier. If we're trying to predict a failure, we need to understand at what point it makes sense to predict a failure and what type of features we would want to use. So here on the right, we see again a few examples of different sensors. And what we can see is that overall, I can tell you that at the end of this window, there was actually a failure in the equipment. And what we would want to do is say, okay, given that there was a failure, at what point could we have predicted there was a change? So if we zoom in on one particular sensor, bit position, what we can think about is if we look at windows of time, knowing that there was a failure at the end of this run, we would want to take windows preceding that failure that would allow us to predict what would happen in the future. What we actually need to do is come up with features or ways to build variables out of this data to then create an actual output that would allow us to predict whether or not there's a failure. So in this particular instance, if we look along the time scale here going left to right, you can see that there's actually a slight increase at the end in some amount of variability there along that actually trend line that we're seeing. Another example here would be with the rotations per minute. As we go left to right, again, knowing that there was a failure at the far right-hand side, you can see again that extreme increase there in the variability of the RPMs that's occurring with time. So if we actually create something like max, mins, look at standard deviations over windows, you could start seeing that from those you could extract features that could then be used to predict a failure. Again, we would want to make sure that we're predicting a failure far enough in the future that it makes sense. So again, just a few examples there, but following up with the final piece, which is around modeling, we have to talk about the different types of models that can be built. The example of an equipment failure, as we just showed before, so given a window of time, can we say what would happen in the future? That's what traditionally is considered a classification problem, presence or absence of a failure. And you might consider using something like a logistic regression, a regularized version of that, meaning that you're trying to penalize for having a lot of features, or support vector machines, which allow you to have a more complex space. Sort of interaction terms be more implicitly included rather than enumerating those. These are just a few examples. I encourage you to check out that general type of I guess that general class of classifiers or general class of machine learning algorithms. Something like predicting remaining life of equipment, that's sort of more on the time scale. That would be Cox proportional hazard regression, something used also in other spaces, including in the medical field. And finally, predicting ROP, that's something where we're predicting a continuous variable, so something like linear regression, elastic net here, similar to the one above, but not in classification and continuous space. And then again, SVMs can be applied in this space in some ways as well. Of course, there are more algorithms not covered, including random forests in both cases. But let's talk through one example specifically about how you do build these types of models at scale. So linear regression, this case of trying to predict a continuous outcome variable, here we'll say rate of penetration. What you want to do is say, given a set of data that I have available, I would like to know if the input variables, for example, weight on bit, would allow me to predict some outcome, the ROP. Now, on the right-hand side, we have an example of what that might look like, where we believe that there's a relationship between weight on bit and ROP. And what we want to do is discover that relationship using all of the input data that's available to us. Now, that might look a little bit like a scary equation, but essentially what we're saying is that given we have these x's, for example, weight on bit, we would want to put some sort of a coefficient in front of that so that we can predict y, our ROP. Now, in school, you might have learned about solving systems of equations where you're trying to solve for it when there is actually a clear answer, but data is never that clean. The world is messy. We don't know all of the variables that are there. So instead what we do is try and estimate what those particular coefficients, those c's, should be in the equation, given that there is not a perfect line to fit through all of these data points. Or if there is, you'd likely be doing what's called overfitting. So there is a closed form solution that we see here on the left to solving this problem, to estimating it. And in essence, what this is trying to do is minimize the sum of squared errors. So what we want to do is pick this line, this purple line through those green dots, so that across all of those dots, the distance to the line, or what we're calling the error, is minimized. Actually, specifically, the sum of the squares of those errors will be minimized. So you're trying to fit a line that is closest to all of the points, optimizing across all points. Now that's actually when you consider that there could be thousands of those x or little x's, so features, and billions of examples. That actually becomes a challenge because traditionally this would be solved on your laptop by loading it all into memory and then going through and solving this equation. Well, that usually doesn't scale. Your laptop probably doesn't have that much memory, not to mention that it might take a really long time. So what we can actually consider is that if we just break down parts of this equation, what we're doing are individual sums and products across them. So here as an example, you're multiplying the feature vector times the outcome variable. Now let's talk about how you might do that in parallel at scale. So linear regression here, if we have an entire, what we're calling feature vector, those are the variables themselves, for example, weight on bit and other pieces, maybe it's the angle that we're using in order to predict y, which is our ROP. Now, to solve this equation, you could actually do those multiplications one at a time and sum them across, or you could actually break that data across multiple segments. That's exactly what we do here at Pivotal when we want to solve these types of problems at scale. So what we do is we use our database, GPDB. We can also use Hawk, which is our SQL on Hadoop, to store all of this data in tables. Rows will now contain all of those, what we call features, so all the individual weights on bit, for example, as well as the variable you're trying to predict, the dependent variable, ROP. What this means is that you can now perform these computations independently, in parallel across those segments. And using the SQL functionality, you actually are also not loading everything into memory once. But what you're doing is scanning the data on the fly and doing that computation as we go through. What that then means is that you're able to go ahead and create that sum without loading everything into memory and by doing that computation in parallel. This is actually part of our open source machine learning library called MadLib. And what we have here is a publication at the bottom, which gives an example of how that scales with, in this example, 10 million rows across multiple segments. We have a variety of other machine learning algorithms that are available, and you can check them out here. Some of the ones that I listed are actually in there as well. Great. So I think it makes sense to move ahead and actually talk about the next use case, vaccine manufacturing specifically. And here we want to address a little bit around the trade-offs between modeling accuracy and timeliness. So in the space of the pharmaceutical industry, there are actually a lot of opportunities for data-driven decisions, and we'll focus specifically on one in manufacturing. Again, manufacturing is an area very rich with sensors along a pipeline of production. You might actually have a lot of those sensors coming in. So let's talk about the example of vaccine manufacturing. On the right-hand side, we have a final product that's going to be delivered to patients. And what we actually have, starting on the left, are some set of input materials that are potentially next going to be mixed together. Those could then be incubated. This was an example that we worked on with essentially used live cells at some point. So those kind of need to be incubated and kept together in a nice and warm environment, controlled temperature, controlled pressure. They might then need to be going through some sort of a filtering step, centrifugation, which is essentially where you spin something in a circle. During that point, you might be collecting more data. So we might be taking, for example, photos at any point of cells. Those types of screens could produce results that a person might look at, or something that would be more automated and looked at. Next, during the incubation phase, filtering phase, and centrifugation phase as an example, data would be collected from the systems. For example, what the temperature was during that time, whether or not things are flowing through that filter at a reasonable rate and what amounts, and again, the velocity for centrifugation. So we want to talk about our opportunities here for intervention and correction. It's a very long process to create this particular vaccine. It takes months. And of course, if at the end of that, the vaccine itself is not of high quality, you would want to know that in advance. So we want to know what the opportunities are along this pipeline for intervention, for correction, to try and fix the particular product before we get to that final stage. How you would want to actually build a model off of that. So how do you take this input data and then decide what features should go into the model? And again, when is the appropriate time to take action? So let's take what happened in this particular example. So on the right-hand side there was our outcome where we had the true potency. That's how good that product is as compared to the predicted one in our model. And again, what we had to go through and consider were all of those data integration, feature building, and modeling components that go into it. So under data integration, of course, we have to trace that particular product through the pipeline. We had to integrate any manual and automated collection data. So, of course, there are some components that are manual, how the particular items were moved around. And, of course, the cleansing of outliers and missing data, which is something that we discussed in the prior use case. Now next, extraction of features. Let's talk about incubation, for example. That's that period where those cells are being put into a nice warm environment to grow. And in those instances, what you would want to look at are, of course, the ways that you want to consider what's happening during that period of time. You might be wanting to engineer features like, again, looking at the mean, the standard deviation of the pressure and temperature through this phase, a median. Some of the considerations, of course, here would be things that are tunable versus just simple measures. So, of course, the temperature can be tuned. Maybe the filtering is not something that could be tuned as easily, but certainly something like an image, counting the number of cells would not be tunable, instead just be a measure. Another consideration, of course, is the step in the pipeline. If I'm predicting something that's occurring very close to that endpoint, so along the 6-month time frame, if it's occurring just weeks before, yes, that might be extremely predictive of the outcome, but that doesn't mean that I'll be able to take corrective action anymore. Certainly doesn't mean that I'll be able to prevent myself from wasting a lot of the time and resources that went into building that particular now faulty and usable product. Finally, we want to talk about modeling. Here are some examples of approaches, algorithms that you might want to use to go after this. including partially squares, random forests, and regularized regressions. You can build many, many features off of this pipeline, but what's important actually is being able, in some cases, to interpret what happened, and certainly being able to know when to have that intervention. So I think one of the critical components that came up in that particular discussion was around tunable versus observational features that you can extract. So here's an example of, at the end of this particular modeling exercise, the types of features that came out as being important. So when using a model that actually allows you to score, or allows you to penalize for having a large number of features, you can reduce that space and actually see which ones come out as being quite important. So in this particular instance, what happened on the left-hand side, we see two different types of features and how they essentially are related to the potency on that y-axis that we're interested in predicting. On the left, we see an assayed value. That's something that cannot be affected. That could, for example, be the size of the cells or the number of them. And if that's something that would, of course, affect the potency, then that's interesting, but certainly it would not be useful to be able to sort of tune it. So meaning that I cannot necessarily make a change here. If it turns out that, the size of something is important, that's simply an observation that I can make that would allow me to have a go, no-go decision made. On the right-hand side, if there's something, for example, the duration of a step that's important, that seems to then affect the potency itself. Since that is something that I can control, we might want to give special consideration to that to try and understand how we can now take corrective action. Of course, in all of this, there's opportunity for more real-time feedback, particularly on the data entry side. So there might be a lot of errors that come out of that, and you could more proactively sort of put in an alert that this looks like it's outside of a norm, something to also consider throughout any of these types of exercises. Great. So now that we've talked a little bit about the trade-offs between accuracy and timeliness, let's finally go over to talking about how to derive insights from models to potentially affect change. Here we'll specifically be talking about healthcare and how you might be able to improve outcomes of patients or increase the efficiency of how you're treating them by collecting data about them throughout their treatment. In healthcare, we actually have a lot of data that's being collected, and if we think about a connected hospital, we do have a large number of sensors that are installed that are collecting data that might predict something like if a patient might crash in the future. So if we can predict that that might happen, maybe we could prevent it. Certainly we might be able to rally up the resources needed in order to make sure that we have the best outcome if such a thing might happen. And that's an example of a use case that we've actually worked on here at Pivotal. So in this image, what we're showing are a lot of the different data sources that are available for patients. Of course, we have their medical history. That includes the diagnoses, what they're sick with, the treatments that they've undergone, the medications, anything around laboratory values. But on the right-hand side, I think we have the much more complex and increasingly interesting data sets that are coming available, including genetic data. That could, of course, be anything that you're predisposed to. It's also being used a lot, for example, in cancers. Images, which of course have been available for a long time, but traditionally have been interpreted by a radiologist and converted into some information. But the raw material itself, the raw images, might actually be useful as well. Of course, what we specifically want to focus on are the sensors here that are available, that are being collected from patients that are being continuously monitored. Now, there are a lot of use cases in healthcare, and we've just got a little bit of a sample here of some of those, including trying to predict if a patient will come to the emergency department using air quality data, again, sensors that are available around us, down to predicting, again, whether or not a patient will have a good outcome, so the early alert of a deteriorating patient. So again, can we increase monitoring there to improve outcomes? I'm not going to go through all of these examples. They're there for you to take a look if you're interested. But really what we want to think about are the particular use cases and what it is that using a different environment might bring to bear in this space. So we'll talk specifically about the use case for these early alerts for deteriorating patients and talk about how using an environment that can leverage all of your data sources, so these sensors in addition to medical history, can actually help build better models here. Of course, talking about using data-driven approaches themselves, so what we've discussed earlier around feature engineering, being able to kind of ask a lot of questions, and finally that insights component, which is the main focus of this particular section. How do you actually interpret your models to influence any sort of change? So a quick overview of this use case and also generally in the medical field what's available to you. Due to the desire in the medical space to support and understand what types of treatments patients are undergoing and they should be reimbursed for, there's actually a rich data set that's available, and electronic medical records are becoming increasingly available in this space. So when a physician treats a patient, they would like to get reimbursed for that particular item. So all of the procedures are actually listed and available to us in this space. And the supporting diagnosis that say why I did this are, of course, also available. What this means is that we have a rich history of what has happened to a patient. And these electronic medical records, in this instance we worked with Epic, store this in an electronic way so that they can be accessed and actually then can be used for data mining in addition to their regular purpose of monitoring patients, understanding what's happening in that environment itself, and of course billing. So this particular project, what we had access to were hundreds of millions of encounters across millions of patients, and they were across multiple hospitals and regions. So in addition to the diagnoses, meaning what patients are sick with, the procedures, what's been done to them, we also had lab values, monitor feeds, and some other data that's important as well, for example, orders that were placed. And we were looking at a hospital setting, again, to predict whether or not a patient would deteriorate. Specifically, if a patient crashes and is not in a unit where they are being closely monitored, for example, an intensive care unit, then the response might not be as good and the outcome would not be as positive. So in this particular instance, we used Pivotal Hadoop with Hawk, which is our SQL engine that sits on top of Pivotal Hadoop. And we also used some R and MadLib for doing the actual modeling. Now what we did, which is something we discussed earlier, was engineer many features for these particular types of models. And actually I need to apologize, this is the length of stay modeling, which is determining how long a patient will be in the hospital when they enter. So in particular, we're actually trying to predict how long a patient would be in the hospital, and the reason why this is of interest is that we need to schedule a discharge time for that particular patient so that they can be taught how to take care of themselves once they leave. They can actually have someone come pick them up, or an ambulance, of course, just transport them. So all of these particular items need to be coordinated in order to make sure that the patient returns home or returns to their next place safely. Now, some of the things that we would care about in these instances are understanding the patient histories. For example, understanding the types of diagnoses they've had in the past, how long they generally stay in the hospital for, knowing whether or not they have certain medications. All of these things can be indicative of how sick or healthy a patient is without actually trying to assess it from sort of an expert point of view of a physician. So there is a lot of data that might support whether or not a patient tends to stay in the hospital for a long time, but also understanding whether or not that's important. So what we did was take patient histories and use SQL to engineer in a lot of those features, looking over windows of time in the past 3 months, year, how many times have you been to the hospital, how long were you in the hospital for, what types of illnesses you've had in the past, how many times you visited a physician, etc. We were also interested in looking at the hospital attributes themselves. It might be important to understand for a particular condition how many of those patients tend to be transferred outside of the hospital and what their experience is in that particular treatment or diagnosis that's coming in. We were focused largely on the heart attack AMI patients. Now, using those particular features, what we did was build a model to try and predict, again, how long the patient would be in the hospital for, and we largely improved the model by engineering a lot of these features and using a lot more of the data that was available to us. But again, the point of this particular section is to actually illustrate how it is that you would be able to influence change in operations. So what we have here on the left-hand side are examples of what happened to the model in terms of accuracy when we removed a certain class of features. So on the right-hand side, again, we have that list of the different classes of features that we engineered. For example, things related to patient demographics in purple, hospital attributes in blue. And on the left-hand side in the bar chart, what we see is when we remove those, the gray there showing the full model with all of those features and the accuracy along the x-axis. So it is the most accurate model. When you remove, for example, hospital-related features, we see a drop. We observe a drop in the accuracy, indicating that hospitals clearly contributed a large amount of the, essentially the data that was supporting being able to predict that. So those were very important features. What's interesting is the patient demographics and some of the medical history in this particular instance for heart attack patients were not as important as laboratory values, information about the current admission, sort of what's happening to you now, or the hospital. What's interesting about that, of course, is we'd like to understand why that's the case. And in terms of the hospital, what we want to do is dig a bit deeper and have a better understanding of why this might be true. So in particular, for predicting how long a patient is in the hospital for, it's not just what's happening in the patient. It also has to do with what's happening in the environment in the hospital, and also other things, for example, the time of day admission, day of the week admission. So being admitted on a weekend means you generally have a longer length of stay. And what we have here on the bottom actually are illustrations of sort of how the hour of the day affects the number of discharges or admissions in this particular space. So on the left-hand side, what we have from midnight to midnight, on the y-axis there, we're showing the number of admissions for heart attack patients in particular. And this is a known phenomenon that there essentially is an increase in the afternoon and a bit of a dip and a little bit of a bump there in the early morning. That's something that cannot be influenced, of course. That's when the patient arrives at the hospital. But on the right-hand side, what we show are the number of discharges, again, from midnight to midnight. What's interesting there is essentially at some point it becomes humane to discharge a patient from the hospital. So you're not going to wake them up at 2 a.m. and tell them to get out, but certainly at some time in the morning it becomes reasonable for them to leave the hospital to be picked up. What's interesting is that we see an increase at that humane hour, and of course that's expected. Someone might arrive, tell them that they're ready to go, educate them on what needs to be done, and then have have someone come pick them up. Now, the challenge, of course, there being that as we move along in the day, we see a little bit of drop and then this huge spike. It turns out that huge spike and the drop as well are influenced by the nurse's shift change. So when the nurses change shifts, everything halts for a bit of time. The nurses communicate to each other what's happening with those patients, and then there is sort of a resuming of that discharge behavior. Now that causes this spike, which of course could cause a lot of downstream bottlenecks, including having people show up to the hospital to pick them up, coordinating any sort of discharge that needs to happen downstream. And so this was something where we indicated that there could be actually some sort of effect or change that would actually allow them to have more positive outcomes in terms of length of stay and not having patients stay longer than needed if that were smoothed out. So again, an example of how actually building a model where something turns out to be predictive can now let you go back and understand a little bit more, create some insight as to what's happening. Now, I only went through one particular example here for the various things that can happen in the hospital. Again, there are a lot of other examples as well. But of course, the promise goes far, far beyond what can happen in the hospital. It can actually also be things that we're tracking about ourselves outside of the hospital that turn out to be very important. So increasingly, we're seeing more sensors that are being introduced. Of course, we have the wearables that we discussed earlier. But those could actually be used for other things as well. For example, tracking what's happening to patients over time that might have some sort of a condition that affects their mobility. Of course, there have been more recent advances in the space of smart contact lenses to look at something like blood sugar drop. That was something that was recently published. And that could alert the patient, of course, in addition to physicians as to what's happening. Tracking patient adherence to some sort of a program, for example, smoking cessation. Interestingly, something like detecting disease outbreaks in the sewer system. So again, using sequencing in that case. Smart chips that can sequence what's passing by and detect organisms that might be indicative of something like cholera in that area. And monitoring on mobile phones, which we mentioned earlier for alerting patients to stroke early on. Now, I didn't have time, of course, to go through too many examples, but I encourage you to check out our data science blog at blogpivotal.io/datasciencepivotal. There are a lot more examples there of use cases across many different spaces, and also include some how-tos on how to do this sort of modeling at scale. So with that, I'll give it back to Bill. Bill, are we ready to take questions? Oh,
yes, we are. I'm sorry. Sarah, thanks for that excellent presentation. We'll get started on our QA session today, and I want to thank the audience for their participation. We have a great many questions that have come in during the presentation, and we'll do our best to get through them all in the time remaining. During the Q&A session, I'll leave up this screen, which has the contact information for Sarah, should you wish to contact her directly following today's seminar. So let's get started. We do have some technical questions to start with, which are kind of fun. For example, can you, Sarah, talk about the methods that were used to capture sensor data and store it in Hadoop?
Sure. So there are actually a lot of different ways to kind of stream that data in. There are examples, of course, across multiple different environments. We have Gemfire, which allows you to actually potentially capture data that's coming off of any sort of machine and capture changes, which then can be pushed down to Hadoop. There are also examples of using something like Springseat to ingest that data as it comes in. We have some examples of how to do that specifically if you want to play around with it. We've done it before with just even using your mobile phone sensors that are on there. In the manufacturing example, of course, they had their own proprietary systems, and that's actually quite common. They might have laboratory management systems. The same is true, of course, for oil rigs. But bringing that data into the environment is generally what is critical, and of course being able to push those changes. So storing that data for any historical purposes is generally best done in an environment like Hadoop, where you can get cheap storage of lots of data of a variety of structure, and you can actually deal with building larger models on top of that. Of course, what's great here is you're able to move forward with pretty much any modeling tool that you're interested in. And again, we tend to think about how to do that at scale in our environment.
Excellent. Excellent. Thank you. You know, we had a request for some additional examples in oil and gas. Do you have any other examples that you could share in oil and gas?
I think, again, I encourage you to check out our blog to see some more of those particular examples. The ones that were highlighted here, we also have a few other talks that we've given. So I think the blog in this instance is the best resource for more information.
Yes, I certainly understand. Yep. You know, to come back to the more general topics, if you are a data scientist, can you speak to a little bit about how one gets started with Internet of Things processing and modeling?
Absolutely. There are some publicly available data sources out there through the UCs, specifically on sensor data. They have a variety of those. Some of them are quite fun, which are, you know, looking at, for example, again, sensor data to try and look at movement. There's one particular data set that one of my colleagues here, Chris Rawls, is working with that was a specific type of wearable. And that wearable itself, the goal was to predict the type of movement that's happening. For example, are you walking upstairs, downstairs? Something as simple as what you have a step counter on your phone, which might seem kind of simple if you look back at the raw sensor data for the velocities in the various planes. It's actually kind of difficult to interpret, and it's actually a great place to get started with trying to classify the type of movement that's happening. So I encourage you to check out those data sets that are publicly posted.
Thank you. And you know, one of the things that I was curious about personally is that I know that in some of these instances, the sensors actually talk to each other. And if that occurs during data gathering, doesn't that create a problem in modeling?
So you're saying that if they speak to each other and they're having some sort of effect on each other, that could have...
Yeah, yes, that's right. There's a dynamic
that you're
relationship.
Then modeling that you're modeling those relationships. Of course, it's always a challenge, the same way that it's always a challenge when you're working with data where you do any sort of cleansing, that you always run the risk of re-identifying some decision that you made. In general, the data that we're working with where they are not speaking to each other yet, for example, the oil rig sensors, or in the medical space, we've worked with sensor data, for example, pulse ox measurements, or any sort of blood pressure monitoring that's happening. Those generally today are not communicating to each other, but if you build the right models, you might be able to also kind of avoid any sort of data by picking pieces that don't necessarily speak to each other, and not rediscover kind of the activities that are occurring. It is definitely a challenge.
Great, thank you, thank you. And there was also a technical question regarding whether or not Pivotal's sequel, which you called Hawk, is the same as Hive.
It actually is not. Hawk itself is essentially a Greenplum database sitting on top of HDFS, so it stores the data directly in Hadoop. Unlike something like Hive, which is actually kind of translating what you're doing into a MapReduce job.
Okay. Yes, I understand. Right. And another technical question comes in. Does MadLib support extra trees classifier and decision tree classifier?
So we do have a variety of tree methods. We have random forest and, of course, decision trees. You can check everything out at madlib.net that we have available. So that's probably your best resource. It can run on top of GBDB, Hawk, and Postgres. So you can try it out on your laptop if you like.
Okay. All right. That seems reasonable. Let's see. I wanted to talk a little bit about one of the things that I run into frequently, and that is you've talked about some examples that have to do with machinery and physical systems, and some other systems that have to do with human behavior. And I imagine there's a lot of difference in the modeling. Can you talk to those differences, especially about the frequency and signs that the refresh might be necessary?
So I think you're talking about how to understand what sort of human behavior could be affected by change, and sort of the fact that you're collecting a lot of sensor data, but that might not actually, continuous feedback is not necessarily useful. And there are certainly a lot of very, very interesting things in this space, thinking about some what's known as alert fatigue. So if I'm getting absolutely too many messages coming in, what's interesting is with the human behavior, trying to affect it and sort of react at the right time. One very interesting case is tracking healthcare workers in a hospital, where there are instances of actually being able to track their movement, sort of where they are in the hospital, and detect that if they've been in one room, that could be done actually by having them wear sensors, but also just by having them interact with the computer on wheels, the cows, so that you know that they've logged into one machine and now they're logging into another. To check whether or not in that interim you can have sensors attached to the actual disinfectants to see if they've actually cleaned their hands between. And that's something very simple where the alerts can come at the right time rather than alerting them up front every single time, hey, you actually need to go wash your hands. It's more you sat down at a computer and I can see that you have not, there's been no activation of any sort of a disinfectant in the meantime. So it's all about, again, that earlier discussion, the alert at the right time and trying to understand when it's appropriate to intervene. Right,
right. We have a question that has come in, and I'm going to have to read it to make sure I get it right. It has to do with your vaccine example, and it's a collection of data from sensors constructed for this purpose were shown in the example about vaccines. However, can the sensors be discovered within the data at transition points throughout the process?
Yeah, so I think if I'm understanding that question correctly, that was actually something pretty interesting in that use case where you wanted to track as appropriately, as you're in the incubation phase, moving into the filtering phase, and then next going into, centrifugation phase. You had to track the particular items. Not to mention those items could be split up and undergo different things. So what's interesting is you actually have to infer a bit of what's happened by the different touch points that you have, and the start and stop. So, for example, in the incubation, of course, that's a room or a space where this is occurring, and many different samples are in there. And so you, of course, have to know that that particular batch of vaccine went in and track only during that period of time because, of course, the sensors themselves around the temperature and pressure are separate from the actual batch. And what you have to do is track entry points where those particular items are put into one environment or another and interpolate what's happening. But absolutely what's interesting is to understand as those items moved, how many times did they move? Were they kept outside of an environment for a long period of time? So it actually is extremely important, although you can't track the individual item, to understand what's happening and what is happening in those environments to try and build sort of features and models out of that.
Excellent. Yeah, I can understand that. You emphasized that you were working with very large data sets, but we do have a question about the concept of the good enough model. Do you start your modeling with small data sets and then work up to large ones, or do you go immediately for the large-scale data modeling?
Yeah, so luckily the tools that we get to work with here at Pivotal allow us to actually work with models at scale, with the data at scale rather. So in a lot of these instances when you're working with a lot of that data, especially with something where it would be interesting to know kind of anomalies that have occurred, that actually in those instances is pretty difficult to work with small data sets because when detecting anomalies, it would be very, very difficult to know that the sample that you grabbed would allow you to do that. However, as we work through this sort of process, often what we will do is do smaller tests to see that what we're doing in terms of feature transformation is correct. But generally, we prefer to work with models at scale. We may actually go through exploration of data, though, at some points on smaller data sets to understand if there are subsets. Certainly see if there are clusters within that data. In terms of understanding if a model is good enough, I can't necessarily speak to a general way that it's fastest and easiest. Again, it's very dependent. It's the classic depends on various factors answer.
Yep, I understand it. And here is actually a fairly similar question. And in the case of parallel computation of linear regressions, the data is divided into segments, and these segments are used to calculate the regressions. So what's the trade-off between using full data sets and segmented data in the accuracy of the model, and how can we validate?
So I think to make sure that I was clear on that, although the computation is being performed on segments, the way MadLib works and the way our team works in general is that we actually don't build separate models. MadLib takes a problem and decomposes it into digestible pieces, which generally means that you're able to perform subsets of that task in parallel across nodes. So ultimately, the regression itself is actually done at scale on the entire model. But what you actually see at the end of the day is sort of that it's being executed across the different segments, but one single model is returned. So hopefully that was clarification. Again, check out madlib.net, and I'm assuming the slides will be made available. So there's a paper referenced as well. There are a couple actually in this space.
Well, Sarah, thanks for those great answers to some very good questions. And for those of you that have asked questions that weren't answered today, we'll be sending all the unanswered questions to Sarah and the Pivotal team so they can follow up with you after today's webinar. So I have just a few quick announcements. Please mark your calendars for August 4th and our next Data Science Center webinar, which is How Do We Know That? An Introduction to Visualization Research sponsored by Tableau. Also, today's taping will be available for on-demand viewing later today and can be found on the homepage of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their participation and thoughtful questions, and a special thanks again to Pivotal for their sponsorship, and especially our speaker today, Sarah Aerni, for insight into today's topic. My name is Bill Vorhies, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on August 4th. Have a great day.